Proton donor receptor.
What we're looking for are hydrogen ions, okay, or our protons. Those are going to be the critical part for understanding this material. Okay? So if you see a hydrogen bound to an electronegative element, you can immediately start thinking, oh, maybe that can be a Bronsted-Lowry acid. If you don't have a hydrogen, don't think that definition. Okay? When we look at the acids, they're proton donors. The bases are proton acceptors. Okay? So Lewis or Bronsted just went through and just based it off of the most simple chemistry, the most available chemistry that they had at the time, which was protons, acids and bases. Okay? Lewis came through a little bit later, said we need to broaden that definition and expand it to electrons. Okay? And so what we're looking at there is the transfer of electrons. That's the easiest to see in lone pairs or charges. Okay? So if you see a negative charge, that's usually a big red flag that you're looking at something to do with Lewis's. Negative charge, lone pairs. What else might stand out for Lewis electron donors? I think someone said it. Yeah, pi bonds. Okay. All of those are kind of things that you can look for within a structure to immediately start to predict something about the chemistry. Okay. If you have an electron donor, so what we look for right away, we're finding electrons. So as soon as you find those electrons, you know you're looking at some kind of Lewis base because it's an electron donor. Okay? The electron acceptors can be a little bit more difficult to find, but those are pretty much going to be anything that's positive that's not hydrogen. How do you get something that's positive?
It's next to something electronegative.
It's next to something electronegative, something that's drawing that electron density away. Okay? The two new definitions, we're going to look at nucleophiles and electrophiles. They're ultimately the same thing as Lewis acids and bases. I'm not quite sure exactly why we use these terms, but we do. So you have to know what you're dealing with. Okay? Your nucleophile is an electron donor. Yes, I did attempt to color code that. Okay? That is the same thing as a Lewis base. Okay? So if you find a Lewis base, it can act as an electron or a nucleophile. Electrophiles will be electron acceptors. Okay? Knowing these definitions and applying them, very similar to what you did with the Bronsted-Lowry acid bases, you're going to have to go through and do that again when we deal with substitution reactions. Okay? For that matter, all reactions. Okay? Let's see if I can get this to work better this time. As far as our haloalkanes, we've already kind of gone through nomenclature a little bit with our halogens. You're looking for primarily the only big difference being the presence of the halogen and having to name it. So you get your fluoro, your chloro, bromo, iodo. Okay, so those are the big things that are added into that. Depending on how you want to name it or how important you think the halogen is in your name, you might end your name with the halide. Okay, so if you thought that the bromide was really, really important and you wanted to accent how important the bromide was to the overall structure, you might name your structure alkyl bromide. Okay? If the bromine plays a secondary role or you want to get more traditional with the naming, that's where you'll go under the haloane ending, okay, if it's just alkanes. Okay? For example, if we take a look at the right, let's take a look at our top structure. How many carbons do we have? You can circle it out. We've got 4 carbons. So our base name would be, so we could go with butane. In that case, we're saying the carbon is our more important thing. We're going more traditional naming here. What's our substituent? Where is the bromo? Put it together and we get 2-bromobutane. If we wanted to accent more the presence of that bromide, we could go through and end our name with bromide. And this one gets messy, but we'll go ahead and do it anyway. That means our bromide is the most important thing. That's our main chain. So we now have to name the carbons as a substituent on our bromide main chain. What's that substituent? If it's butyl, the bromine's attached to the first carbon. So you came up with an IUPAC name. I don't want to write the IUPAC name. We could call it sec-butyl bromide. Or, as you were starting to say, we could do 1-methyl propyl bromide. If we wanted to go.
Those are all the same options.
Those are all the same name. Okay? Kind of makes sense? Pick one method and stick with it. I tell you, I preference that top one, going 2-bromobutane. I think that's a little bit more straightforward, easier for me to read, easier for me to grade. Okay? Questions about that? So let's try the last one. How would you name this one? We've got our main chain, which is 4, so we're looking at butane. What's our substituent? A chloro. Where's the chlorine attached? Position 1. So we could call it 1-chlorobutane, or because it's at position 1, we can just drop it from the name, and it's chlorobutane. Okay? Kind of makes sense? Okay, so all the complications of your alkyl naming, now you have to add in halogens as a substituent and number and name accordingly. Okay? The next part that's a little bit more important here is looking at the reactivity. Okay? What do we know about halogens? In particular, halogens compared to what atom? What atom am I going to compare my halogens to if I'm going to look at my alkyl halides? Why carbon?
Because it's always what we look at.
Not quite. It's what it's bonded to. Okay? What we're trying to do is see how that chlorine or the halogen changes the reactivity of the structure. So I want to look and evaluate the bond where the chlorine is attached or the bromine is attached to the overall structure. Okay? So when I compare a halogen to carbon, what's our simplification for our halogens? They're always more electronegative than carbon, which means if we look at dipoles, we could draw a partial negative charge on the chlorine and a partial positive charge on the carbon. Okay? What does that mean as far as reactivity? Well, if I've got a partial positive charge and it's not on a hydrogen, what do I have? I have an electron acceptor, which means Lewis acid or an electrophile. So we can now refer to the reactivity of that carbon as electrophilic. It wants electrons because that chlorine is taking them away from it. Okay, so it needs to find an electron source somewhere else within our solution. Okay, what about the halogen? It is negative, but how many bonds can our halogens have? Just one. It already has that one. So even though I do have those extra electrons, it's not going to be very easy for that halogen to give up those electrons to another atom while still staying attached. Okay? So as far as the reactivity goes, when we look at our alkyl halides, pretty much the only thing we've got is that our carbon is electrophilic, or a good Lewis acid. Okay? The next fun thing that we can always think about is our physical properties. It's kind of a secondary role as far as organic, or as far as the lecture class is concerned. If we compared chlorobutane to, say, pentane, which one would we expect to have a higher melting point? I had to make it pentane to account for kind of the weight difference. So we're looking at approximately the same weight. Why would the chloro have a higher melting point? The partial charges generate a polar covalent bond, which means dipole-dipole force, which is a stronger force than our London dispersion forces from just the carbon and hydrogen. And because of that stronger intermolecular force, we get a higher melting point or boiling point. Okay? So it all keeps coming back to these things that we've already looked at before. Kind of makes sense? Okay. So let's see what we can do with it. Hopefully I didn't ruin it. Uh-oh, I may have just pissed it off. Okay, so what we're going to do now is start to look at what we can do with these different reactions. Okay? So let's go through and look at each of these pieces. I know there's all sorts of weird letters in there, but let's just kind of treat those as a group and see what things have changed in each case. Okay? So when you take a look at that first line, what's changed as we've moved from a reactant to a product? Has anything changed? So you notice the lone pair. Interesting thing to note. That's cool. I can accept that. If we take a look, yeah, I might as well stick with that. The lone pair seems to have changed places. If we take a look at our product, the nucleophile, or the Nuc, is attached to the carbon, not to the metal hydrogen. Okay, what else has changed? Well, what happened to our LG? It's also changed positions. Okay? In fact, we could say they exchanged places, or we did what's commonly referred to as a substitution. We don't look at it as an exchange anymore, where in Gen Chem you'd probably look at it as a double replacement or something along those lines. Here we're only concerned about the organic molecule. So when we look at the organic molecule, what happened to it? A piece was substituted, was exchanged for something else. So what we've got there is a substitution reaction. Okay, does that kind of make sense? Identifying the pieces that have changed as you move through it and just seeing what happened. How about the next one? What happened in the next one? What things changed there? That one admittedly is one of the more difficult ones. Yes? So that's interesting. The LG is completely broken off. It's no longer attached. Okay, and I've got a double bond. What else changed?
Hydrogen left in the attaching piece.
I've also got that hydrogen. Where did that hydrogen come from? Nope. How many bonds does this carbon have? Our red dot carbon. We only see 2. There has to be 4, which means there are 2 hydrogens. Where's that carbon in your product? The carbon. Right there, right? How many bonds are shown to that carbon? 3, which means there's only 1 implied hydrogen. Where did the other hydrogen go? Okay, it was picked up by our base. So it's trying to identify those pieces and see what things have changed. Okay? This reaction, we lost something. Okay? Or we eliminated something from the overall molecule. Hence we get the elimination reaction, hopefully what I'll cover on Wednesday. Okay? The last one we'll cover after spring break. What happened there? Okay, we formed some new bonds. We broke that bond, broke that bond. We started with 2 pieces, and now we have 1. We added 2 things together. We've got an addition reaction here. Okay? So what we're starting to see is how we can put these things together. Yes, it's made a little bit more confusing with those extra letters and colors, but those are there intentionally. So substitution and elimination are ultimately in Chapter 7. You'll see them a lot in Chapter 8 as well, because Chapter 8 is looking at alcohol chemistry. Alcohol chemistry is based largely the same as our alkyl halides. Okay? And then Chapter 5 is really the addition reactions. Okay? So what I said today is we were going to look at just our substitution. Okay? So what we want to go through and do is start to learn something about how this reaction occurred. Okay? And at this stage, all I'm doing is specifying those with fairly vague terms that you may not know yet. But what we're trying to do is see what those pieces can do. So with all reactions, we should identify our bonds broken and bonds formed. What bonds were broken? Okay, we broke that bond. What else did we break? Okay, we broke that one. Did we break any other bonds? Now, do we form any bonds? What bonds do we form? Okay. What class was this again? Organic chemistry. Which compounds in here are the organic ones? Probably the one with the black line, right? So that's going to be the thing we're focused on. That's where all of our energy is going to be involved in. Okay? So when we look at that, we're trying to break the bond between our carbon and our leaving group, and we're ultimately making our carbon nucleophile bond. So as far as we're concerned in organic chemistry, we're looking at only two things happening. Okay? So now that we know what's happened, we need to try and come up with a way of how it happened. Okay? And that's when we look at mechanisms. So this is pretty much the beginning of mechanisms. The rest of the semester, this is all we're looking at. Okay? So if you've got questions, it's good to slow it down now. Okay? So what we want to do is figure out how these bonds were broken or formed. Okay? There's a big hint to help out with this, or a couple big hints. I'm going to tell you that there are 3 possible ways that this could happen. Okay? I'm going to take it a step further. I'm going to tell you what way number 3 is as a possibility, and then you guys can help me figure out the other 2 methods. Okay? I'm going to go ahead and form my carbon nuc bond first, and then break, was it a carbon lug bond? That was just fun to say. Okay? How else could I possibly do those 2 important steps? Okay? And like I said, we're only concerned about those steps because it's just organic chemistry. We just want to look at the organic molecules, at least at this point. We could go through and instead of forming the carbon nuc bond, we can break our carbon lug bond. You should try it. It is actually kind of fun to say. And then form our carbon nuc bond, or all at the same time. So let's see how familiar you guys are with organic chemistry. How many types of substitution reactions are there? Just a test, just to see. Okay, it turns out there's only 2 possible mechanisms when looking at this. I've got 3 possibilities here. Seems a bit odd. Okay, so what someone went through and did is just did the numbers game. What are the possible combinations that this could possibly occur in? You get all 3 of these options. We then go back and say, okay, I know a little bit about organic chemistry. Let's see if any of those are even physically possible. Okay? And as a big hint, let's go ahead and take a look at number 3. Is it physically possible to form that carbon nuc bond and then break the leaving group bond? Why does that not physically work?
You have to be simultaneous. There's only one pair of electrons to
If we formed our carbon nuc bond first, that's what we'd get. What's wrong with that drawing? 5 bonds. What does that mean? 1/3 the amount of work we have to do. We don't have to worry about step 3, right? Okay, step 3 is not physically possible. Okay, which means we're now down to 2 possibilities. If you go through and look at your possible substitution reactions, or even that quiz, you'll see, remember back on the homework part, people were asking questions. What does SN1, SN2 mean? Well, S stands for substitution 1, type 1 reaction. SN2 stands for substitution type 2 reaction. Okay? So, cool, I didn't. So before we move into actually drawing out these mechanisms, tried to hope to piecemeal, but that didn't work out nicely, we can define each of these terms. Okay? So when it comes to a substitution, and for that matter an elimination reaction, we've got ultimately 4 big pieces. You've got your substrate, your leaving group, which I abbreviated as LG. your nucleophile, which I abbreviated as the nuc, and then you've got your solvent. You're responsible for understanding what changes to each of these things can occur, and how does that determine which reaction predominates. Do we get the SN1 type or the SN2 type? Okay? So you need to have some understanding for each of these individual things. The substrate structure, it usually contains the electrophilic, or it definitely contains the electrophilic carbon, and in the starting material it also has the leaving group attached. Okay? Your leaving group is the atom that takes the electrons away from carbon. Okay? Kind of important as far as this chemistry goes, because when we looked at alkanes, we were just having hydrogens attached to our carbons. Would we expect a hydrogen to take electrons away from a carbon? No, why not? It's less electronegativity, or less electronegative. Okay? So when we move up to alkyl halides, we can increase that reactivity because we can add in chlorines and bromines. Those elements can take electron density away from the carbon, and at the same time they leave with the electrons, hence the leaving group. Okay? The next part is our nucleophile. What was the definition of a nucleophile? It was an electron donor. So when we go back and take a look at what I had drawn for the nucleophile, someone actually pointed it out. You've got the lone pair. And in the process of the reaction, the lone pair disappeared. Did it really disappear? Where did that lone pair go? It made that carbon-nuc bond. Okay, because remember, the leaving group took the electrons away. We now don't have electrons for that bond. The nucleophile must supply those electrons to make that new bond. Okay? H and the M. H stands for hydrogen. Okay? We'll get into those exact details, but if you see an H attached to your nucleophile, you're looking at an SN1 type mechanism, typically. Okay? And that's because we make that bond weaker, or sorry, stronger. That bond is now a little bit stronger when I've got a hydrogen. Why is that important? Well, what happens when I move to the SN2? I put element M. What's element M? It's a metal. Metals don't share electrons. Their electronegativities are so low that they just give up their electrons right away. So when we go back and look at our nuc structure at the top, instead of the nuc just having a lone pair, it ends up gaining another lone pair, and it becomes negatively charged. That negative charge is a big red flag for the SN2 type. Okay, again, we'll get into the details of that. Okay, so depending on what is attached to your nucleophile, you may see it push different mechanisms. Okay, the last thing is our solvent. We aren't going to look at as much at solvent. I do expect you to be able to pick up certain definitions from it. For the most part, your solvent is something that's there to kind of facilitate the reaction. Okay? We never add a solvent that would harm the reaction, but what we could do is choose our solvents to prevent one mechanism over the other. Okay? So we can pick and choose how our reaction is going to work depending on what solvent we use. Okay? You've already heard of polar and nonpolar as far as solvents. We're going to add a new definition to that, and that's protic and aprotic. Protic sounds like, or prot sounds like proton. What you might expect for a protic solvent? Any guesses for an example protic solvent? Hydrogen's not going to be quite protic. Right idea. We need to attach that hydrogen to something to stabilize it. Something electronegative. Water is a perfect example of a protic solvent. Something that's willing to give up H+. Okay? Comfortable with the pieces? Okay, so what we'll do now is actually look at the mechanism. Like I said, I wanted this to stepwise into it, so it looks like a bit much at first. So we'll go through it kind of slowly. Your substitution, the N stands for nucleophile. We needed a nucleophile for this reaction to work. Okay? That'll become a lot more important when we move into the elimination reactions. You'll notice there's no N when we look at our eliminations. Okay? Our substitutions require a nucleophile, and in this case we've also added this term unimolecular. We'll come back to that as well. Summarize the two things that had to happen. We have to break the leaving group bond first, and then we have to form our carbon nuc bond. Okay? Try to make this reaction as generic as possible. Sometimes it takes a little bit less steps. Okay? So to start it off, we need to break that carbon leaving group bond. Okay? So what we're going to do is have the leaving group take the electrons away from the carbon. Why does it take the electrons away? Our leaving group is always more electronegative. We're typically looking at our halogens. So what it's going to do is take those electrons. So what we're showing is that that pair of electrons in the bond go to the leaving group. How do we know we've moved the pair? We look at the arrows. It's a double-headed arrow. Okay? That's all we're doing in our first step. Okay? So we can now draw our reaction arrow. In this case, I'm moving downwards. And we'll draw the result of that. Our carbon lost electrons to the leaving group, so it's now going to have to be positively charged. Okay? Our leaving group just gained electrons. Well, if it gains electrons, it should be negatively charged. Okay? At this stage in the game, this is probably one of the more critical steps. Okay? We've got some highly reactive species. How do we know these species are reactive? They're charged. Okay? So our very first step is not a very easy one. We're going from something that's uncharged to something that's charged. Not a very favorable thing to do. Okay? We're increasing reactivity. Okay? Because that positive charge is something we don't want, we need to stabilize it. How do you stabilize a positive charge? You give it electrons, so we have to look for somewhere within the reaction do we have electrons. We had two options. We've got the nuke or we have the leaving group. The leaving group has a negative charge that can absolutely share its electrons with the carbon. What happens? It goes backwards. So if you look at the arrows that I actually have drawn in between each of these, you'll notice they're equilibrium arrows. They do go backwards and forwards. Okay? The leaving group attacking isn't the nicest thing, so let's do something different because that's more fun. Let's have the nuke attack. So we'll take the lone pair from our nucleophile, and instead of being a lone pair, I now want to share that with my carbon, okay, particularly that carbocation. And so we'll take the electrons starting from my nucleophile and draw them towards the positive charge. Okay? Step 2 of my overall reaction. Okay? What happens as a result? Well, the rest of my carbon chain didn't change. The carbon, though, that was positive just gained electrons, which means should be neutral right now. What happened to our nucleophile? It gave up electrons. It started neutral, lost electrons, so it's now positively charged. Okay? Also still not particularly stable. How can I stabilize a positive charge? It's going to need to get electrons from somewhere. Okay? It's a problem with generic things. We don't want to just bring in the electrons from our leaving group as something like that, because that means that nucleophile has to form another bond. You'll find in the non-generic cases that it can't form another bond. Okay? So it's got to get the electrons from somewhere else. Okay? And in most cases, there's an easier place to get electrons than from somewhere else in the solution. Where's that easier place? Close. Something closer than the hydrogen atom. The bond between the nucleophile and the hydrogen. So what I'm going to do is take the electrons in that bond and give them to the nucleophile. So what I've shown is that that bond now breaks. That bond now breaks. It was a good thing I wasn't drawing anything, right? Okay, that bond ends up breaking. And what ends up happening in that case, we'd have H plus floating around. Not a bad idea to try and stabilize an H plus. What do we need to do to stabilize H plus? Give it electrons. Our leaving group is negative. We can have that negative pair up with our positive hydrogen. Okay? And we end up with our final product. You'll notice I added a third step. This third step of removing that hydrogen is something you typically only see in the SN1 reaction. Okay? It doesn't always show up, but it occasionally shows up. Okay? It's done to help stabilize, or it's done just because our nucleophile, in the case of the SN1, isn't very strong, okay, or typically not very strong. Okay, so you may or may not see that. What type of reaction occurred to go from that, our nucleophile hydrogen state to our final product? We did form a bond between the leaving group and our hydrogen. We also broke a bond. What type of reaction? It's an acid-base reaction. Most acid-base reactions happen extremely fast, so it's very often that we tend to ignore them. If you guys remember the aspirin lab, when I drew out all that mechanism stuff in lab, you got a lot of acid-base reactions happening on and off, allowing us to move one direction or another. Okay? So try to not get bogged down in the acid-base extra reactions. Realize that we do want to finish off our reaction and take it to the neutralized state, okay, as best as we can. Okay? You will see that show up in your homework. Questions about this reaction?
So how does the nucleophiles go positive when it has the lone pair already?
So it went positive because of this step. We took that lone pair and we shared it with something else, which means it has effectively lost an electron to that carbon atom. So if it loses the electron, it becomes positive. In our last step, we can neutralize it because it can take the electrons away from our hydrogen. Does that make sense? Other steps with the overall mechanism, or questions with the overall mechanism? Okay. Of these mechanistic steps, which one do you think is the slowest? Why the first one? We're creating charge. If we look at our second step, we actually neutralize charge, effective or sort of. Kind of just shift it around. So ultimately, we aren't really changing things too much. In our very last step, we completely get rid of the charge. Okay, so our first step ends up being the most important step. Those of you that have taken Gen Chem second semester, if our first step is the slowest step, we would also refer to it as... Anybody taken second semester Gen Chem? Okay. Typically referred to as our rate determining step. Is that writing? Okay. RDS, or rate limiting step, RLS. So if we were going to look at a rate for this reaction, we're going to be concerned about what's happening in that first step. Everything else is irrelevant. Okay? So when we go through and look at our, oh, I drew that wrong, dang it. We look at our first step, okay? Which part of that am I going to be most concerned about? The products of my first step or the reactants? This might go out to the Gen Chem 2 people. We're really only concerned about the reactants. The rates of reactions are dependent on the concentration of our reactants. The products very rarely feed back and slow down the reaction. It happens in biology all the time, not necessarily in chemistry. So what we want to do is take a look at this very first step, and I want to figure out how fast that step can occur. Okay? Well, the speed or the rate of my reaction should be dependent on my reactants. Okay? How many reactants do I have in that first step? Okay, you say 1, you said 2. What are your 2?
Well, I changed it to 1.
Is this a reactant? So this is where it gets tricky. This is a reactant. Is it reacting in my first step? No. What is reacting in my first step? Only this. It becomes 2 pieces, but it's not 2 pieces yet. It's only one thing. Which means if I'm going to look at the rate of my reaction, it's going to be dependent solely on the concentration of this species. Okay? Which is why you can tell there was a typo now. If you look in the lower left-hand corner, our rate is going to be determined based on some rate constant and only the concentration of the substrate. The nucleophile is not important in the SN1 reaction. Okay? Questions about that? Okay. SN1, where did the 1 come from? What's that? Unimolecular, referring to, Gen Chem 2, referring to the number of species in my rate law. How many species are in the rate law? Only one. So I'm looking at a unimolecular reaction. That's where the 1 comes from, SN1. Okay? When we move to the SN2 reaction, we're breaking our leaving group bond at the exact same time as we form the nucleophile bond. So when we go through and look at our overall reaction, I'm going to take the electrons in that carbon leaving group bond, and I'm going to give them all to the leaving group. Okay, so I'm taking those electrons and shifting them towards the leaving group. There's our arrow. So that's the breaking of that bond. But I have to make the nucleophile bond at the exact same time, which means I'm going to show the nucleophile coming in and attacking that carbon, helping the leaving group leave. So in a mechanism, I only get one step. I go from my reactants immediately to the products. Okay? Yes, there's some weird dynamics on that. I'll discuss that in a second. Okay? So instead of having to deal with all sorts of different steps within it, we get one thing straight across. You'll notice also here I've shown sodium, which is a metal. When we move to the SN2 reaction, we're looking at metals typically with these. We're looking at very strong nucleophiles. Why would I need a strong nucleophile? Has to overpower the leaving group is one possibility, which is ultimately a good one. Let's go through and evaluate just like we did for the last one. We want to know how fast our reaction goes. Which step is our rate limiting step? There's only one. Okay, so that first step is my rate limiting step. Okay, how many reactants are involved in my rate limiting step? 2. It's going to be dependent on the concentration of my substrate and the nucleophile. Why do I care about the strength of my nucleophile? Because if I have a good, strong nucleophile, my reaction goes faster. Okay? So we've started to develop and evolve some of the rules that come along with each of these. Okay? For the SN1, we didn't really care about the strength of the nucleophile, which is why we have a hydrogen attached to the nucleophile. That's a stronger bond than if I attach a metal, which I do for the SN2 reaction. Okay? So where you guys might all be looking is why did I not talk about that stuff in the middle? Okay? This does show our mechanism going straight forward. Okay? But it doesn't represent or allow us to see the dynamics of what is actually happening around our reaction site, our electrophilic carbon. So what we can do is draw what's referred to as a transition state. Try to use goofy arrows, because those are goofy, as opposed to reaction arrow, because it's not officially a reaction. This species does not exist. We're only using it to represent what's actually occurring in the reaction. So we usually pick brackets, put it around it, and put up a double dagger. Okay, the double dagger is saying that we're at a transition state. This is when we're shifting from reactants to products. Okay? When the nucleophile comes in, you'll notice that I had it come in from this side, right? Why did I not have the nucleophile arrow, for instance, come in from up here? Or say from over here? Why does it need to be opposite the leaving group?
Those will both be negatively charged. They want to be as far apart from
The leaving group is negative, the nucleophile is negative. What happens when they get near each other? They repel away. So our nucleophile must come in from the back side of our carbon leaving group bond. Okay? So the term that everybody remembers with our SN2 reaction, it's almost always referred to as a backside attack. Ha ha ha, right? Okay? Our nucleophile has to come in from that angle. We get too much electron repulsion if the nucleophile comes in from any other angle. Okay? Does that make sense?
Is that where you get things like frequency factors? Like the frequency of an atom striking at the right angle? That's what it is.
Yes. Yeah, that's where you can get some frequency factor stuff, yeah. Okay? So let's take a closer look at the drawing that I've got down here, the transition state. If we take a look at that carbon, okay, let's assume the leaving group has left. How many things would be attached to that carbon? So, 2 hydrogens in the bond, so we've got 3 things. So what I can do is take that structure and rotate it up out of the plane. And what I'm trying to show here, though did a very unsuccessful job, we can make those hydrogens. Our nucleophile comes in from the back side, pushing the leaving group away. So our structure starts at a tetrahedron. Our nucleophile comes in from the bottom of that tetrahedron, pushing out the leaving group and breaking my hand. Okay, as the groups pop up the other direction. So you get what can be seen as like an umbrella in the wind. Okay? An important distinction to make when we actually push some of the complications of these. Questions about our SN2 reaction? Okay. The rest of these slides are going to be referring to each of the individual pieces or aspects of each of these reactions. Okay? So, substrate classifications. We want to come up with some way that we can quickly refer to an individual substrate and pin down something about its reactivity. Okay? When we looked at the... actually, I don't want to go back. Please don't go back. Didn't go back. Good job. So when we look at our overall reactions, we want to know where our halogen is located. So this is where you can get the terms primary, secondary, tertiary, which I think we briefly talked about. Yes, no? Primary, where our halogen is attached. The carbon to which it's attached. You're going to go to the next slide. That wasn't very nice. And it's disconnected. Come on. If we take a look at the carbon to which it's attached, how many carbons are attached to that carbon? Our red carbon now has just 1. So, primary. How many carbons are attached to our next carbon? We have 2. Hence we get secondary. We move to the last one, you get tertiary. Methyl, just because I feel like mentioning it. If we were going to draw out a methyl, we could draw it out like this. We've got a carbon with 3 hydrogens attached to it. We're going to hold our primary, secondary, tertiary rules. That would be called... Nothingary doesn't sound as cool, but not a bad guess. Zeroary, because it's attached to 0 carbons, right? Okay, so you might hear zeroary or methyl. I thought it was funny. You'll laugh when you go home and listen to the lectures then. Okay? So we need to be aware and cognizant of what we're referring to when we look at our substrate classifications or our substrate rankings. The next thing that we could look at is the leaving group. Its ability to leave. Its ability to take the electrons away from the substrate. Oh, okay. So, leaving group, ability to leave, take the electrons away from the substrate. Okay? So, why would something take electrons away from a carbon? We already looked at one answer. It's electronegative. It needs to be able to take the electrons. But once it's taken the electrons away, it also must be stable. Okay? And that gets a little bit trickier. If it's not stable as a negative charge, what happens? It goes right back to our substrate, and we don't get our substitution reaction to occur. So when we're looking at leaving group ability, it has to be able to minimize that negative charge. Okay? So what kind of a species would we be looking at? It's likely going to have electrons. Could be an ion. This is a similar pattern as we've seen before. Say in our acid-base chapter. A strong acid was strong because its base, its conjugate base, was weak. So when we're looking at leaving group ability, we want something that is very weakly basic. Okay? So you can go through and rank varying leaving groups according to their base strength. If they're a really strong base, what does that mean about their leaving group ability? They're not very good leaving groups. Okay? So we're looking at electron withdrawing. We're trying to polarize that carbon bond. Okay? But it then needs to be stable once it's left. Okay? That's where we get this weak base from. There's a couple lists, or there's a list here of ions that are good leaving groups. Your halogens happen to be great ones. Okay? You can see a bunch of other groups that also act as good leaving groups. We can also see neutral molecules. Why would a neutral molecule be a good leaving group? What's our number one rule? What does it have to be able to do? It must minimize the negative charge. If it's neutral, how negative is it? It's not. That sounds like a pretty good neutralization of a negative charge, right? Okay. So we can generate leaving groups that are neutral depending on the circumstances we're looking at. We'll see that with our alcohols. So we'll see water as a good leaving group when we move into Chapter 8. Okay? Right now we're primarily concerned about our chlorides, bromides, and iodides. Why is fluoride not a good leaving group? I know, I threw that one out of left field. Chloride, bromide, and iodide are all pretty good. Why? They're larger and they're electronegative. What's the issue with fluoride? It's small. Okay? So we've got essentially a point charge. Point charge is bad. We need to spread that charge over a larger area to stabilize it. Okay? So it's not just based on electronegativity. We're looking at basicity, or weak bases. Okay? And in fact, in this case, incredibly weak bases. Okay. Punch developers. Our nucleophiles, the next piece. Our nucleophiles must be electron donors. Okay? What's a big red flag for something that's willing to donate electrons? Okay, a base. But if I just throw out a random structure, that doesn't necessarily help you out. Could be something that's on the very top of the list. Okay? If it's negatively charged, it definitely has a bunch of electrons. Why? That's why it's negatively charged. Okay? So typically, negatively charged species are stronger nucleophiles than the counterpart. So if we go through and compare, we actually get some examples going through here. Hydroxide versus water. Which one's the stronger nucleophile? Hydroxide, because it's negatively charged. Okay? So with each of those cases, we're looking at progressively making it more and more difficult to determine our nucleophile. The next one, we're typically seeing nucleophilicity decrease from left to right. Okay? Lower electronegativity means more electronegative. Sorry. Yeah, let me try that again. Lower electronegativity means more nucleophilic. Why does that make sense? So if I compare hydroxide to fluoride, based on our first rule, they're both negative. Why would I expect hydroxide to be a better nucleophile than fluoride? What's the difference between hydroxide and fluoride? Where's the negative charge in hydroxide? Careful. It's on the oxygen. You'd have to draw out your Lewis structure to make sure you see that. So we're looking and comparing oxygen to fluorine. Size, they're both in the same row, so not a bad first guess. The electronegativity is different. What's the difference in electronegativity? Fluoride is the most electronegative element, which means it does what to its bonding electrons? It keeps them. What does the nucleophile need to do? Donate them. Okay? So if you have a good nucleophile, it's typically going to have a lower electronegativity. The next two are a little bit less common. For sure, I'm not going to test you on the solvent effects. If you're interested in looking at some of these, you can take a look at them later. Okay? But solvent plays a huge effect on nucleophilic strength. Okay? So I won't have you rank things where size becomes an issue. Okay? And that's ultimately our solvent dependence. Okay? So our nucleophiles, we're concerned about negatively charged and nucleophilic. Okay. Next thing that we will have to evaluate is steric hindrance. That's going to play a larger role when we move into the elimination reactions. Typically, the smaller our system, the more nucleophilic it is. The bigger it is, the less nucleophilic it is, and the more basic it becomes. Okay, and we'll evaluate that when we look at our base strengths. Okay, our solvent classifications. Now we can kind of breathe. This one's a little bit easier to work with. Okay, what roles do our solvents play? Okay, our main reason to use any solvent is to dissolve all the compounds we're working with. Okay, so it's all in the same phase. Once it's in the same phase, we can increase the interaction between those compounds. It helps things out. Okay, after that, it can stabilize intermediates. It can also destabilize intermediates or reactants. Okay, so remember that when we look at the SN1 reaction, we get to stabilize intermediates. The SN2 destabilizes some intermediates, depending on what solvents you choose. Okay, so we have to pick our solvents appropriately for each mechanism. So what defines appropriately? Well, we've evaluated polar versus nonpolar before. We're going to add some extra definitions to this. And that new one is the one we're calling protic versus aprotic. Okay? All we're saying is that we have a hydrogen bound to an electronegative element. And in particular, a hydrogen bound to oxygen, nitrogen, or fluorine. Also known as what kind of a solvent? A hydrogen bonding solvent. Okay? So if you have a hydrogen bonding solvent, that is a protic solvent. We could also call it polar. Okay, so we look at that. That's water is a good protic solvent. We could also call it polar. Is it necessary to add the polar term to that? No. Why not? Protic, by definition, has to be polar. So it's not necessary to add that extra term. Most people do, but it's not strictly necessary. We can also have a solvent that is polar but aprotic. So it doesn't have the ability to hydrogen bond. Okay? Those are our two primary solvents, protic and our aprotic. Okay? We can push to nonpolar aprotic. There are a few cases of that. We typically don't work with those because, any ideas? When we looked at our SN1 and SN2 reactions, did you see any charges? We see any positives and negatives? How do you stabilize a positive and a negative? You need more positives and negatives to be able to balance it out. What kind of solvent is going to supply those? One that's polar or one that's nonpolar? One that's polar. Okay? Our nonpolar solvents don't really work for our SN reactions because they don't stabilize any of the intermediates. Okay? Or they won't dissolve them. So we got a couple examples of solvents on the right. Okay, let's take a look at that first one. What do you think? How would you classify that one? So you go polar versus nonpolar first. Nonpolar. Why would we do polar versus nonpolar first? We don't have to worry about the other definition. Okay, so we're looking at a nonpolar solvent here. So I can go with just N for that case. How about the next one, ethyl acetate? Polar or nonpolar? Polar. Why is it polar? Because there are oxygens in there. Okay. Is it protic? No. So we have a polar aprotic solvent. How about acetic acid? Has to be polar because we got the oxygens and protic. How do you know it's protic? We do have that oxygen and hydrogen. How else can we look at it? What was the name again? Acetic acid. Acids by definition give up, also known as protons. If you have an acid for a solvent, it is by definition protic. Okay? Get the idea? Should we try one more? How about lower right? Dichloromethane. Polar versus nonpolar? Polar because the chlorines. Protic versus aprotic. Aprotic, where are those hydrogens bound? To a carbon. Okay, so we're looking at a polar aprotic solvent. Kind of makes sense? Okay. Now I think we get to get into the fun stuff, in my opinion. Bring it all together. Okay, SN1 details. What was the very first step in our SN1 reaction? All the way back at the beginning of our notes. We had to break the carbon-leaving group bond, which resulted in what? A positively charged carbon. For this reaction to work, that very first step must occur. That positively charged species is unstable. So if I want this reaction to go forward, I need to stabilize that positive charge as best as possible. Okay? And that's where we're going to get into carbocation stability. So we could go through and look at all of the other things attached to that carbon. Okay? So first off, before we push into any of those questions, well, never mind, all the answers are up there. How would we classify our first structure? It's a methyl cation. It's a cation, so we've got, or a carbocation. We're looking at the groups attached to it. They're all hydrogens, so we can refer to it as methyl. Okay, if we looked at the last one, what's happening there? 3 carbons attached, we've got tertiary. Okay, so you'll hear me refer to tertiary, primary, secondary, zeroary carbocations. This is what I'm referring to. Okay, so in the SN1 reaction, I need a stable carbocation. Okay, so what makes each of these things unstable? Positive charge. So if I want my SN1 reaction to work or progress forwards, I need to somehow stabilize that as best as possible. So now that we know what makes it unstable, how do I stabilize it? I need to give it electrons. Where are there electrons? In the leaving group, but that's already left. Could also even push the nucleophile, but that hasn't come in yet. Starting to hear it? What does that line represent? A bond which represents electrons. So I've got 2 electrons in that bond. How many electrons in that bond? How many electrons in that bond? Cool, 6 electrons around that cation. I like that. That'll help stabilize it. Let's check here. Not a bad idea, but it didn't quite work. Okay? So if we don't find a difference, what should we do? Move further away. What's the next thing out? Carbon. Okay, what's the next thing out? Shoot, I should have gone this way. What's the next thing out up here? Hydrogen. Is there a difference between hydrogen and carbon? Yes. What's the difference between hydrogen and carbon? Sorry, what were all those? Okay, electronegativity. Is there much of a difference in electronegativity between those? No, we pretty much say they're equivalent. That's why we call them covalent. What else was different? Size. What does size due to? Right idea. How do we get bigger? We get bigger because we add electrons. So when we go through and evaluate these, carbon, down in this bottom case, has how many valence electrons? How many does this one have? How many does this one have? So what do we have? We've got 12 supporting electrons. Okay? We can't do resonance, but we're just saying there's 12 electrons around that carbocation. How about the next one? How about the next one? And the last one? Which of those carbocations is going to be the most stable? The tertiary. Why should the tertiary be the most stable? It's the one with the most electrons around it. Okay? So if I'm going to predict an SN1 reaction and I want to look at a starting material and I say, this is my starting material, would I expect... I'm not drawing anything, am I? Did it erase everything? Did I just talk through that with no writing?
just waste. Everything else is up there.
It's always fun when I draw and nothing happens. So shall we try again? What happens with, yes? What would I expect for this reaction? If that was my alkyl chloride, would I expect that to be promising in an SN1 reaction? Yes. Why? Because when the chlorine leaves, what does it leave behind? It leaves no electrons, positive charge left on what kind of a carbon? Tertiary. Okay? So when I look at my SN1 mechanisms, a tertiary alkyl halide is a good thing. That's probably going to push in SN1 direction. Secondary also works. How about primary or zeroary? There's so little electrons around those carbocations that they cannot be stabilized, and we do not predict any reactivity for them. Okay? Just to throw it out there, let's see how well you guys are doing with this. Until everybody's kind of giving me the stink eye, so this probably won't go well, but we'll see. That actually pop up. Which of these is the most stable now? Tertiary, secondary, primary, zeroary?
Zeroary.
Okay, what makes each of those unstable?
Too many electrons.
The negative charge. How do I stabilize the negative charge? I have to get rid of it. Okay, well, I can't really get rid of it because then it wouldn't be the negative charge anymore. So what I need to do is find some way to stabilize that negative, or rather not destabilize it further. Okay, so I could try and bring in protons, but again, that's bringing in something else. So the thing that's going to determine stability here is the one that has the least amount of electrons around that negative. Because the more electrons I put in one area, the more reactive it becomes. Which of those has the least amount of electrons around it? Our zeroary. So our zeroary anion is more stable. Okay? SN1, some more kind of detailed summary on this. So when we look at our substrate, okay, these are all, again, kind of intentionally vague here. There's a better summary at the very end of this. We just talked about our substrate. What makes a good substrate? We want to generate anything that makes a stable carbocation. So we could go with something tertiary. We would expect to react faster than secondary. And we said our primary and zeroary won't react at all. Okay? How else could we stabilize a positive charge? Everybody's favorite word, the R word. Resonance. Okay? So when you draw out your carbocations, you might want to evaluate, can you stabilize that structure through resonance? Okay? Which means, can you push electrons to it from somewhere within the structure? When we're looking at our leaving group, okay, I know this is written really, really vague. It should be good. Okay? It just pretty much has to be a good leaving group. If it's not a good leaving group, it's not going to work. Okay? So there isn't a whole lot I can add there. When we move to the nucleophile, we typically classify the nucleophile for the SN1 reaction as weak. Why did we say the nucleophile needed to be weak? What's that? Which step was our rate determining step? The first step. Do you see the nucleophile in our first step? No. So do we care about the nucleophile? No. So when we're looking at our reactions, we can classify based on substrate structure. Leaving group is going to be consistent for all of them, so it's not going to be all that helpful. But we can look for our nucleophile next. If we have a weak nucleophile, that's probably going to favor an SN1 reaction. How do we know it's weak? What's that? Ish. Showed it way back at the beginning. Strong base is actually a strong nucleophile. Better. If we have a hydrogen attached to our nucleophile, we're probably looking at a weak nucleophile. Okay? Really, it's easier to identify the strong nucleophile. What's going to be a good strong nucleophile? First rule, not positive, but negative. If it's negatively charged, it'll be a strong nucleophile. It has the electrons to be able to donate. Okay? The last one, which is the trickiest one, solvent choice, polar protic. Okay? Why would a polar protic solvent be helpful? Okay? Our first step was the one that we said was our rate determining step, our slowest step. That's in the formation of our carbocation. Already given you a hint here with this drawing. What hybridization is a carbocation? sp2. Okay? So if we drew that out again, let's draw it not shown with the p orbital on it. How many groups of electrons are around that center carbon? 3 electron groups, which means sp2. The positive charge is replacing that last electron group. Because I don't have electrons in that orbital, there's no need for me to hybridize, and I get a leftover p orbital. So if we take our carbocation with our p orbital that in this drawing is coming in and out of the board at you, and I now turn that structure, I end up with this drawing. You guys see that? Not at all? Okay, I'm getting some yeses, so for the no's, you can talk to me after class. Okay? That positive charge, this is where this one gets tricky. Our nucleophile can come in either from the bottom and attack the bottom p orbital or the top of the p orbital. When it does that, that generates 2 different products. What's the relationship between those products? R and S. Okay? So we end up with a racemic mixture when you go through an SN1 mechanism. Why do we care about a polar protic solvent? We want this first step to occur, which means I need to stabilize the heck out of that carbocation. How can I stabilize a carbocation? With something negative. What does a polar protic solvent generate? We already talked about one part of it. If it's protic, it has hydrogen, but it's a hydrogen that is partially positive. How do we get a hydrogen that's partially positive? Let's attach it to an oxygen, nitrogen, or fluorine. If it's oxygen, what's special about oxygen? It's incredibly partially negative because it's electronegative. That partial negative can stabilize our cation. That's why we use the polar protic solvent. Okay? And since the stereochemistry thing kind of threw you for a loop, I won't move on to the next one. Okay? So the last, I think, probably 6 or 7 slides, 4 or 5 slides, we'll finish up on, I should probably stop recording.